Distributed large language models. Prompt: if you look at the task manager of your PC, you will probably see that neither the CPU nor the memory is utilized 100%. This is probably true of the millions of PCs in use all over the world. Since many of those PCs are connected to the net, they constitute a vast reservoir of unused capacity. This capacity could be harnessed to create massive AIs. How would we do that? Response introduction. If you open the task manager on your personal computer, you will probably notice something surprising. Even when running intensive applications, neither the CPU nor the memory is fully utilized. This reality is not unique to your machine. It is true of millions of PCs in use worldwide. Collectively, these underutilized machines represent a vast, untapped reservoir of computational capacity. Since most of them are connected to the internet, they form a latent network of distributed resources that could, in principle, be harnessed to create massive AIs. The vision is bold. Instead of relying on a handful of giant data centers operated by tech giants, what if the world's idle PCs could be pooled into a planetary-scale computing fabric capable of training and running large language models? This essay explores how such distributed systems could be built, the challenges they face, and the revolutionary implications of making AI a truly global, shared resource. The hidden potential of idle computers. Modern PCs are extraordinarily powerful compared to even high-end servers of a decade ago. A mid-range laptop today may feature multi-core processors, 16 to 32 gigabytes of RAM, and high-speed storage. Yet in practice, most users run workloads that rarely saturate these resources. Web browsing, word processing, video playback, or even gaming rarely drive CPUs and memory to 100% capacity for extended periods. When multiplied across hundreds of millions of machines worldwide, the scale of this latent capacity becomes staggering. Conservative estimates suggest that even if only 10% of idle resources were harnessed, the total would dwarf the capacity of the largest existing supercomputers. Projects like SETI at Home, https chair.setiathome.berkeley.edu, and Folding at Home, https foldingathome.org, proved decades ago that distributed volunteer computing is feasible. But unlike those projects, which focused on scientific simulations, the new frontier is AI, specifically distributed training and inference for large language models. The concept of distributed LLMs. A distributed LLM is one in which training and inference are not confined to a single supercomputer or cloud cluster, but rather are spread across thousands or millions of geographically dispersed devices. In such a system, each PC contributes a small slice of computation, processing a batch of data, storing model shards, or serving inference queries. This is analogous to how BitTorrent distributes file sharing, or how blockchains maintain consensus across a decentralized network. Instead of a central data center, the AI would live across the network, drawing strength from the collective power of participating machines. Importantly, the users donating compute could themselves benefit. In return for their contribution, they might gain access to the AI, earn digital credits, or receive monetary rewards. How would we do it? First, model sharding. Large models contain billions of parameters, making them too big to fit on a single PC. However, the model can be partitioned, sharded, into smaller segments. Each machine stores and processes only its shard, while communication protocols coordinate the forward and backward passes of neural network computation. This idea is already used within data centers, e.g., model parallelism in GPT-style training, but could be extended across the internet. Second, federated training. Federated learning provides another template. Here, the model is copied to many devices, each of which trains locally on data, and then sends back gradient updates. The updates are aggregated into a global model without centralizing raw data. Applied at scale, federated training could enable millions of PCs to collaboratively refine an LLM. Third, decentralized inference networks. For inference, running the model to generate text, distributed networks could use peer-to-peer architectures. A user's query could be broken into smaller subtasks distributed across nodes, with the results recombined. Alternatively, shards of the model could be loaded dynamically from nearby peers, reducing latency. Fourth, incentive structures. A critical challenge is motivation. Why would individuals lend their computing power? Incentive mechanisms could mirror those of cryptocurrencies, tokens or credits issued for compute contributions, exchangeable for services or currency. This would create a market for distributed AI compute, balancing supply and demand dynamically. 5. Security and reliability. Distributed computing raises concerns about malicious nodes or faulty outputs. Techniques like redundancy, sending the same task to multiple nodes, consensus protocols, and cryptographic verification would be essential. Advances in zero-knowledge proofs might even allow nodes to prove that they performed a computation correctly without revealing sensitive data. Technical challenges. 1. Bandwidth and latency. Training LLMs requires massive communication of gradient updates and parameter states. While cloud data centers are optimized with high-speed interconnects, the open internet is far slower and less reliable. Clever compression, sparse updates, and asynchronous training will be required. 2. Heterogeneity. PCs vary widely in CPU power, memory, GPU availability, and internet speed. Scheduling tasks efficiently across such diverse resources is non-trivial. Systems must dynamically assign workloads based on capabilities. 3. Privacy. If local data is used, e.g., for personalized AI, ensuring user privacy is crucial. Federated approaches and differential privacy mechanisms will be essential. 4. Fault tolerance. Nodes may disconnect at any time. The system must seamlessly adapt, redistributing workloads and ensuring continuity. 5. Energy and heat. Running AI workloads consumes energy and may strain consumer hardware. Careful throttling, opt-in participation, and compensation models are required to prevent backlash. Why bother? The benefits of distributed AI, democratization of AI. Today, only a handful of corporations, OpenAI, Google, Anthropic, Meta, can afford the billion-dollar infrastructure needed to train state-of-the-art LLMs. A distributed model would shift power away from centralized entities, enabling communities, researchers, and smaller companies to collaborate on AI development. Resilience. A distributed system is inherently more resilient than centralized data centers. Attacks, outages, or censorship affecting one region would not disable the network. Efficiency. Rather than letting unused computing power sit idle, it could be put to productive use. This repurposing of waste capacity is both economically and environmentally attractive. Innovation. Opening participation to millions of nodes worldwide could accelerate experimentation, with different communities training models tailored to local languages, cultures, and needs. Future scenarios. 1. Global AI grid. Imagine an electricity grid for AI, where compute is treated as a public utility. Individuals and organizations contribute resources and, in turn, gain access to collective intelligence. 2. Personalized AI training. PCs could train local submodels on personal data, emails, documents, health data, and contribute generalized updates to the global model. The result would be AIs that are both personal and collective. 3. AI as a commons. Just as Wikipedia is a shared global knowledge base, distributed LLMs could become a shared global reasoning engine, owned and governed collectively rather than by corporations. 4. Hybrid architectures. In practice, the future may combine centralized and distributed approaches. Large companies may still host the core model, while distributed nodes handle personalization, fine-tuning, or inference load balancing. Lessons from predecessors. SETI at home and Folding at home demonstrated the feasibility of volunteer compute networks, but they also revealed limitations, inconsistent participation, lack of incentives, and reliance on centralized coordination. Blockchain networks, in contrast, showed how cryptographic incentives and decentralized consensus can sustain massive distributed infrastructures. A future distributed LLM system would likely need to blend these lessons, the scientific rigor of folding at home with the incentive mechanisms of blockchain. Conclusion. The idea of harnessing millions of idle PCs to build distributed large language models is both technically challenging and profoundly transformative. While bandwidth, security, and heterogeneity issues loom large, the potential benefits, democratization, efficiency, resilience, and innovation are immense. As AI becomes a central force in human society, the question of who controls it will matter more than ever. A distributed approach ensures that intelligence is not the exclusive domain of tech oligopolies, but a resource cultivated and shared by humanity at large. In many ways, this vision echoes the early spirit of the Internet itself, a decentralized network of peers, cooperating to create something greater than the sum of its parts. Just as the idle cycles of millions of PCs once helped search for extraterrestrial signals, they could now help build the intelligence that shapes our collective future. The question is not whether we can do it, but whether we choose to, because the infrastructure is already humming quietly in task managers across the globe.